We're going to have two invited speakers again. I'm happy to introduce Marija Popović. She's a junior research group leader at the University of Bonn and part of the Cluster of Excellence PNARUDE. Before starting her in Bonn, she was a postdoctoral research associate at the Smart Robotics Lab at Imperial College and received her PhD from the Autonomous Systems Lab at ETH Zurich. Her research is centered around developing algorithms to enable intelligent decision-making for autonomous mobile robots, both aerial and ground. Her research group focuses on furthering robot autonomy in agricultural applications with topics that span from planning, coordination, environmental mapping, computer vision for decision-making.
So thanks again for the introduction, and thanks to the organizers for inviting me and taking care of the hybrid setup. So my name is Marija Popović. I'm a junior research group leader at the Cluster of Excellence PNARUDE at the University of Bonn. And it's a great pleasure to be here today to talk about our work on mapping and planning for robotic decision-making. Now, before I start, I want to give credits to the PhD students in my junior research group, Liren and Julius and Jonas, who have contributed to this presentation with their work and materials. So our talk today is about robot autonomy. So let's have a look at the scale or spectrum of autonomy and how robots play a role on different levels. So consider a situation without robots in the game at all, where everything is done fully manually and completely by humans. So there we see some examples of human doing weeding operations on a farm, inspecting a bridge, and so on. Now, when robots enter the picture, we use them typically in a fully manually controlled way. So what we're mostly familiar with these days is using a joystick to control a robot or some kind of app interface to get primitive operation. And this is what most people use these days. However, fully autonomous robots work in different ways. So in these situations, we want to really exploit the fact that robots are programmable devices, and then they can reason about their surroundings and make informed decisions and even cooperate. And this way, we move away from simply using them to replace what we already have in a one-to-one way, but we want entirely new workflows with robots doing things by themselves. So there are some examples where the robot needs to interpret the state of their surroundings, reason, make high-level decisions, and then plan paths in order to complete their missions successfully. So today's talk, we're going to be discussing new algorithms that allow this type of behavior. And specifically, we're going to focus on the application of active sensing. So where should the robot look next in order to perceive its environment best? And as we see, we'll focus on the particular application of UAV-based terrain monitoring. So now that we understand what we're trying to do, let's build up the structure of an autonomous system to see how this can be done. So this is a general structure that is applicable for any robot in an active sensing scenario. So we assume that a robot is equipped with a sensor, for example, a depth camera or multispectral camera from which we can extract measurements. During a mission, we use these measurements to build a map based on a model of the environment. And at this stage, we might also have some prior information from previous missions that we want to incorporate. Then during the mission, we have a planning algorithm that uses these maps to generate new trajectories for the robot to complete its mission. And here, a key ingredient is the so-called utility function, which captures the aim of the mission. So what we want the robot to do or to sense. So utility functions can look, for example, like inspecting a certain plant on a field in a targeted way, detecting victims in a search and rescue scenario, and so on. So now that we understand the general overview of the system, we're going to discuss methods in each of these components that allow robots to achieve this type of behavior. So let's start with the mapping module. So as we said, we focus on mapping fields or terrain. So what are some of the specific challenges associated with mapping these types of environments? Well, typically we have large fields areas that we want to cover and sensors which provide very high resolution measurements. For example, high resolution cameras. Meanwhile, if we're doing some sort of processing on the images, such as semantic segmentation, as shown here in an example of crop weed segmentation, we might also have uncertainty that we want our map to capture. And finally, given the nature of the environment, there might also be some spatial correlations that we also want to take into account. For example, given the clustered nature of the ways in which plants grow. And the main challenge is how can we incorporate all these elements into a single, compact, probabilistic map representation that is suitable for being updated online during a mission when new measurements arrive, as well as for online planning. So I wanted to introduce mapping method for continuous variables that caters for these needs. So as we said, we want to map continuous variables. So some scalar function on a field, you could imagine that takes a real value. You could imagine like temperature, elevation, vegetation density, and so on. And here we use an approach called Gaussian process or GP fusion. Essentially, we use GP to initialize a prior map of the environment. So that's the box on the top left. And then when new measurements arrive from the camera sensor, given their uncertainty, we fuse them into a map recursively using a Bayesian fusion procedure. And more details about the technical can be found in the citation, but for our decision-making application, such an approach offers important advantages. So first, because the map is at a fixed resolution and is only initialized with the GP at the beginning, we can get constant time updates, which is fast and important for real-time applications. And second, as we can see from the box with the measurements, the approach supports variable resolution and uncertainty. So we can map with heterogeneous sensors, which is also very important for practical robotic applications. So a key question that we asked in this setup in a work that was presented at IROS 3 days ago now is how can we adapt the map resolution to further conserve memory and computational resources? So the intuition behind this is similar to what we do in Octomap, where we essentially use a tree structure to group information where values are similar to save resources. So how can we do this in the setup of GP fusion that we have? But if we want to do this, we realize that it's not that trivial because of these spatial correlations that are captured in the GP itself. So we have a mean and covariance from the GP model. And when we try to merge cells, as shown in the example in the map, so there we try to merge this 4 dark blue cells into the lighter one, we need to preserve the correlation behind the smaller cells in a theoretically sound way. So how can we do this? One important theoretical contribution of this study is the integral kernel function. So to understand the integral kernel, one can think about what do we know about a regular kernel in machine learning, which is defined on points. So essentially a kernel based on the covariance captures how 2 points in the model relate to each other or their correlation. And the integral kernel is essentially the analog of this, but for areas. So if we have 2 areas of the map, how are they related? So we can use this mathematical operator. And by applying this, we can thus merge multiple cells into a larger one while preserving the correlations as well as the mean values. This is a bit of math to describe a mapping approach that can be deployed online, but it hopefully becomes clear with an example. So let's start with a synthetic example. So on the left, we can see an experimental setup of simulation environment with the UAV and the continuous variable field, as well as the ground truth. And say in this setup, we want to map the higher valued areas in more detail, so at a finer resolution. So these are the yellower ones. So if we apply the adaptive resolution approach, we can see that indeed we get high resolution in these yellower areas of interest, when we can compress information in the low resolution areas while also preserving the spatial correlations. So this is a further improvement to the efficiency of the approach. Now, in this workshop, we're interested in real-world applications and deploying robots for practical scenarios. So we also tested this on real-world data for validation. So there is an experimental setup of the UAV equipped with a thermal camera that was flown on a field close to our university, and we collected thermal imagery. The bottom left shows the thermal orthomosaic that's generated. So we can see some variations in the temperature distributions. The redder areas are high temperature and bluer are low temperature. And now applying the same logic from the simulated example, we want to map the higher valued areas in more detail. So this is what the mapping output looks like. And looking at the grid lines, indeed we see that finer resolution is obtained in the warmer areas, while we compress information in the less interesting, the bluer, cooler areas. So there is a video to illustrate this, how this actually works in practice. So a UAV is flying a lawnmower pattern. The data is real world data. There is a different field that was imported into the simulation environment. And when the UAV receives the measurements, it dynamically adjusts the map resolution based on what it sees. So based on what the values are. And one can also think about defining different objectives for mapping. For example, say we want to map lower values in more detail, then we will get the opposite kind of behavior. So that was a mapping method for decision making. So the question is, how can we then use the maps to plan informative or useful paths for the robot? And then we get into the planning algorithm and studying utility functions. So how can we define more precisely the objective in an active sensing application where a robot is intelligently taking measurements? So in literature, as some of us may know, this is called the informative path planning problem. So say we have the UAV with the camera, as in the mapping examples, that's flying and collecting some measurements. The informative path planning problem tries to maximize the information gain in new measurements collected during a mission, subject to a budget. And that's what the equation is trying to say. So in simpler words, how should the UAV fly in order to get the most useful data from the environment, given its limited flight time? So we want to maximize the limited budget to get the best mapping performance. And objective functions can look like, for example, mapping high temperature areas, as we saw an example, or mapping weeds in more detail, mapping specific plants. But can also be mapping victims in a search and rescue scenario. So this approach is difficult for conventional planning techniques for many reasons. So first, importantly, we have to predict the value of future actions before the robot actually executes them. So we need to reason about what will happen in the future, which is difficult. And moreover, what makes it even more difficult is that we typically in real-world applications have unstructured environments, very complex, high-dimensional problems, and we need to evaluate the possibility of many such actions. And what makes it even harder is that we have computationally constrained platforms with limited resources, and we need to develop algorithms to cater for this. So one solution, this problem can be approached from many ways. And one solution I want to discuss is how we can cater for these requirements and especially computational efficiency using deep reinforcement learning, or RL, based on work that was presented at ICRA. So the approach works as follows. So we have a neural network, which we see on the left, which learns the best policies for the robot to execute. So the best data gathering actions. And we train this network based on a realistic simulation environment shown on the right, where we simulate many diverse terrain monitoring scenarios, varying the spatial distributions of what we want to observe. And then based on a tree search technique, we update the weights of the network such that it learns the best data gathering actions. And in this way, we effectively learn using deep RL where the most useful measurements are to be found. So why would we want to use RL for this application? Well, I hinted at computational efficiency. So the main advantage is that given an already trained network, we only need to deploy it using a single forward pass. So we don't need to use models to reason about many potential candidate actions and worry about the search space given this problem, but we have a learned network and we can deploy it to circumvent this. So we showed this, here's some experimental results to convince us that is the case. So we compared this in simulation, and there are some different benchmarks and evolutionary optimization routine based on previous work, Monte Carlo tree search, which is commonly used for such problems, a coverage baseline, which is similar to what we saw in the mapping example, so executing a zigzag pattern over the field, as well as random waypoint selection. And then on the left, we can see how the map uncertainty evolves during the mission, while on the right, we see a runtime comparison. So looking at the red curve on the right, we can see that with RL, we obtain fastest uncertainty reduction by some margin, but most importantly, we can get a very quick speed up on online replanning for predictive planning, which is very important, as we said, for real-time applications. Okay. Yeah, so actually in recent work, we're, no, sorry. So again, real world example, I got a bit distracted. We also tested this using real world data. So using the same setup as before, again, we collected a thermal orthomosaic from the field, and then we tried to deploy the RL approach trained in simulation to see what happens. So we said we have a mission where the objective is to map these high temperature areas with more measurements. So to make it interesting, so to map things in a targeted way. And we compared what one would commonly use in practice, which is coverage planning. So typically we have a commercial drone and we generate some lawnmower path with an app. How does it compare with the RL-based approach? So we see a significant uncertainty, quicker uncertainty reduction with RL because of this targeted capability that was learned. We can also confirm this qualitatively by looking at what the trajectory of the UAV looks like. So as we would expect, once it has explored the environment, it focuses on collecting more measurements, more data on the high temperature side, because this is what we defined our objective function as. And now we're also considering how this can apply to multi-UAV applications in a very early and ongoing work. And this problem is even more challenging because in addition to where an agent should measure next, we also need to consider team behavior. So how should the agents behave cooperatively while also replanning efficiently? And we're investigating the potential of state-of-the-art multi-agent RL algorithms and transferring them to the robotics domain through this application. The main idea is quite similar to the single agent case where we try to train a network and then deploy it online to improve efficiency given the already learned network parameters. So there are some subtle differences with respect to the single agent case, but I will just avoid them for the sake of time. So now I want to present a slightly different approach to the informative path planning problem, where we actually use decision-making to learn how to improve a model in a new environment. And this application is, I think, very interesting for the workshop because it connects different parts of robotics, robotic mapping, planning, and learning. So here we focus on using active learning. And the problem setup is one of aerial semantic segmentation. So as we know, semantic segmentation is an important tool for understanding and observing the Earth. So there are some examples of urban aerial imagery. But we also know that training supervised deep learning models for semantic segmentation is extremely time-consuming and laborious. So given the examples, we can see various classes, for example, buildings, foliage, and cars. And one can think if you were to sit down and trace the fine contours of all of these objects, you would get frustrated rather quickly and also bored. So how can we use robots to alleviate this, to minimize labeling effort? That's the main idea, using informative planning combined together with an active learning strategy. So let's build up the method and the system pipeline. So say we start with a network deployed on a UAV that is pre-trained for semantic segmentation. And here we use ERFnet in our approach, which is a very computationally efficient method suitable for these computationally constrained applications. Then, if the UAV is flying and collecting some images, we run forward paths through the network to obtain semantic labels as well as the model uncertainty. And then, given these images that were collected at a particular instant, we project them based on the UAV pose on a global map of the environment, which captures these variables. So there we can see maps of semantic labels and model uncertainties for a trajectory that was executed, and it's clear how we can see the history of observations. Then, given the result of the online inference, as well as the current state of the global map, we try to plan future paths for efficient trained data collection. So how do we do this? So the key idea is to link the informative planning objective to active learning. So active learning essentially tells us that the most uncertain images to be collected are the most difficult examples for the network, and thus hold the most value when added to the training data set. So in other words, we want to collect most certain images, reasoning that they have the highest informativeness. And then when we plan paths based on this concept in the utility function, when we collect new images, we can only pass those images to the human annotator for labeling so that the network can be retrained after the mission. So here are some results of how this works. So just to understand the figure, our metrics are on the x-axis. We have the number of images that is collected during a mission. And on the vertical axis are measures of model performance for semantic segmentation. So here, the steeper rising curves, or the ones on the top left, essentially capture better performing planning strategies. So we compared the lawnmower coverage type of path, which is often used as the baseline, as we saw, against various informative planning strategies. So I won't go into the details about how each of these strategies are implemented. It's a study of planning algorithms, and I refer to the paper which was presented yesterday at IROS for a detailed description. But importantly, based on the image, we can see that indeed informative planning for active learning does push us to the top left so that we can actually collect useful training data more quickly and save labeling effort. And an interesting finding here is that our fixed horizon planning strategy, which essentially plans multiple steps ahead based on the map state, performs the best. And this kind of justifies the combination of planning, mapping, and learning in this approach. So there is an example of how these different components can be integrated together in a single system for a very practical robotic application. So that slowly brings us to the end of the talk. So we started talking in a general way about robot autonomy. Then we specified on this active sensing problem, focusing on UAVs and how we can generate efficient data gathering missions. Then for each component of the informative planning framework, we discussed different methods for achieving this in terms of mapping, continuous variables, reinforcement learning, and also an application of combining informative planning and active learning. But obviously, it doesn't end here. This is just some methods for achieving active sensing and using informative planning in practical applications. But there are obviously many open questions that I want to encourage the workshop participants to think about. So for example, if we have dynamic or moving objects in the environment, how can we incorporate that in the map? How difficult does our problem become? Can we do something more like continual learning, so continuously improving the model in new environments rather than collecting images, retraining after? And an important practical consideration is localization uncertainty. So if we're not that confident in the robot state estimation, what actually happens to the map? Does our planning system completely break down? And so on. I'm sure there are many more open areas of research and ideas. So that's it. Thank you for your attention, and I'm happy to take any questions.
Thank you, Marja. In the interest of time, Ruben, could you already come to the front? But we have time for a few questions, so please go ahead if you have any.
Thank you for your talk. What are your thoughts on long-term mapping for these field areas where we cannot extract a lot of the structure? And also, what are your thoughts on using artificial landmarks in these kind of cases?
So what is the second question?
Using artificial landmarks in the field for mapping and localization.
Okay, so the first question is about long-term mapping. So I think, so basically in these applications that I presented, it's mostly about small platforms that can fly maybe 15, 20 minutes, something like this. So the way to do it best is, I think, if we have multiple missions and then we collect some data and then we use that as a prior for a new map. So that was also kind of captured in the informative planning framework where we had the prior box. So I think that could be one way of doing it, because I think with the current systems or the ones that we're tackling for such applications, it would be impossible to fly many hours and continuously update the map. I think it's super interesting problem though.
But I was thinking more about through the year, because crops grow up and then the volume changes and the map changes basically. So.
Yeah, so you could capture maps for different years, and then maybe you could use the previous map at that season as a prior, and then you have at least some expectation of what things may look like, but then you obviously maintain your previous data and you can do a comparison and maybe capture some trends. So like doing a spatial temporal analysis, I think that's very exciting.
And using artificial landmarks just for
yeah, I think so. We haven't used them, so I can't say from a practical point of view, but I think it can be, it could maybe help with the localization part, because then you could use them somehow to localize better. Thanks for the questions.
Hi, so thank you for the talk. For your reinforcement learning approach for the path planning, have you investigated sort of how adaptable that is to different scenarios? So for the temperature mapping case, it was tested just on a field, how that would apply to a sort of urban data set or like a more forested data set, that kind of thing?
I think so. The reinforcement learning approach is also very map dependent. So the example I showed is mapping continuous variables. So if you have a variable that looks like the one that you trained on and has a similar spatial distribution, I think it would be kind of variable agnostic. We haven't tested it, but from what I know about the continuous mapping with the spatial correlations, that would hold true. But then if you have like, I don't think you could deploy to the urban mapping scenario out of the box, because it's just too different. And you also have different inputs, because on one case you have measuring some scalar continuous variables, and on the other hand, you have discrete categories of class labels.
Thank you.
Thanks for the question.
Thanks. I'll ask a quick question. I think it's something that you probably already touched upon. So there's a lot of environmental phenomena belong to a spatial temporal field. Do you have any comment or any suggestion about how to deal with spatial temporal mapping?
Like that vary in a short term?
Yeah, the varies, for example, dispersion driven by the wind field, or like a temperature field that may change because you transfer from daytime to nighttime, the temperature will change naturally, right?
Yeah, so the key assumption in the work is that the variables do not change. So I don't think, again, you could apply out of the box the methods that were presented, but you could make some adjustments to the way you represent your map. For example, adding some kind of model of what you expect your changes to be. That would be just one simple way of incorporating that.
Thanks. Yeah.
Thanks.
Thanks a lot for the talk. Very exciting work. One issue that we oftentimes ran into when doing active perception with something that includes a neural network in the sensor model, that it's really hard to predict what the network will see at different points in space, in particular in the unknown areas. So you solved this by using uncertainty. Do you think there's other surrogates or ways these sensor models can be modeled for deep neural networks? Or can they just implicitly learned in RL maybe?
I haven't thought about it that carefully. I mean, this we did the uncertainty thing there, and we also had the data set that we could, this Potsdam data set of urban mapping, where you could kind of divide the train, test, and validation classes into reasonable splits so that you get kind of expected performance. But I think that would be an open research question.
Great, thanks.
Thank you.
Thanks again to Marija.